Medias in res. In this video, we will take a closer look at the things that are happening inside a computer. That is how data is processed and what is happening during the execution of a computer program. Let's start with an automaton. Imagine a simple beverage dispenser. It is clear, if you insert a certain number of coins and select a drink by pushing the corresponding button, you will, in the best case, get the selected drink as an output. More general, there are input elements and output elements. And there are processing steps between input and output, which are usually not visible. We have discussed input and output for a simple automaton. But what kind of input and output does a computer receive or produce? It is quite simple. You feed the computer with data, or more precisely, commands, for example, via touchscreen, mouse, keyboard, or microphone. Then the computer outputs, for example, a message on the screen or a sound. We can conclude, data is processed according to the IPO model. IPO stands for input, process, output. We will now take a closer look at the processes inside the computer. To understand this, we first have to focus on the components, the so-called hardware, of a computer. Our simplified computer consists of 6 parts. Let's start with the CPU. The CPU, which is short for Central Processing Unit or simply processor, is the brain of the computer. It performs all operations and consists of several parts. The control unit, or simply controller, generates the control signals for the other components of the CPU and the computer. The arithmetic logical unit, or short ALU, consists of auxiliary and status registers and a combinational circuit that performs the arithmetic operations. A register is a memory and its content can be accessed super fast. Here we see a schematic figure of the CPU. The arithmetic logical unit consists of 8 registers, R1 to R8. The program counter is a register which contains the memory address of the command that has just been fetched from the main memory by the control unit. The program counter always points to a memory address in the main memory. The CPU understands machine language and can execute a machine program. The program and the data that needs to be processed must be located in the main memory. The main memory is often referred to as RAM, which stands for Random Access Memory. The CPU can directly access a specific content of the main memory with the help of the corresponding memory address. First, a machine instruction is fetched from the main memory into the CPU and is then executed. The results of the computation are returned to the main memory, where they can be retrieved by the output unit. The main memory does not contain any programs or data yet. But we will change that soon. Let's continue with the bus system. The bus system of a computer is responsible for transporting data between the individual units of the computer. The external bus or expansion bus is responsible for the data transport between external devices like a monitor, printer or USB stick and the main memory. The internal bus, also called data bus, system bus or frontside bus, is responsible for the communication between the main memory and the registers of the CPU. To keep it simple, we will only talk about the general bus, where data get on the bus, go with the bus and leave the bus in the end. One thing is still missing. So let's look at the interface for the input or output devices. The input unit forwards inputs to the computer by passing them on to the bus. From there, the input first goes in the main memory. The output unit is used to convert the computed results into something that humans can read or recognize. For example, a signal on the screen, a printed document, or a sound. It receives the data from the main memory via the external bus. And last but not least, we need a memory where we can store data and programs permanently. The hard disk is one example of a permanent storage. Information stored on the hard disk remains there even if the computer is switched off or in case of a power blackout. A program that is stored on the hard disk cannot be executed by the CPU. To execute the program, the operating system has to move the program from the hard disk to the main memory. Enough of the theory. Let's write our very first program, which should then be executed by the CPU. The program should compute the area of a square with the length a equals 5. To solve this arithmetic problem with the help of a computer, we need to know its set of instructions. Different CPUs have a different architecture and therefore different instruction sets. The instruction set is a set of all the instructions the CPU can process. For our example computer, these are the 8 valid commands that can be processed by the CPU. This is our test program. It consists of 7 commands to compute the area of a square with a specific length. To check whether the program computes the area correctly, we have to execute the program. Initially, the program is located on the hard disk. But how does the program get into the main memory? Imagine that the program can be started by double-clicking on a corresponding icon on the desktop of your computer. Now double-click on the imaginary icon. This will load the program from the hard disk into the main memory. A certain address range in the main memory, also called user space, is made available to the program. The first command of the program is added to the house with the address S1. The second command is added to the house with the address S2, and so on. The program expects an input, namely the value for the length a of the square. A should be 5. This input is done by default via the keyboard. So the number 5 gets on the bus and travels to the main memory, more precisely to the house with the memory address S0, the standard input. In our example, the memory address S0 is used for all inputs and outputs. Now the first command gets executed. The program counter must point to the first command of the program. The arrow symbolizes the content of the program counter. The value of the program counter must be set to S1. The command the program counter points to is now fetched into the CPU and gets executed. The command the program counter points to is now fetched into the CPU and executed. The execution of the command causes the input, that is the number 5, to be stored in the house with the memory address S8. The program counter is incremented by 1 and now points to the memory address of command S2. The command is now fetched into the CPU and gets executed. It causes the value stored in the house with the memory address S8 to be written to register R1. Remember, registers are also memories. The program counter is again increased by 1. The corresponding command is fetched into the CPU and gets executed. When the CPU executes the command write S9, the value stored in the house with the memory address S9, that is the number 25, is written to the standard output. This means that the number 25 is stored in the house with the memory address S0, or the standard output. The result, namely the number 25, is then, for example, displayed on the screen. After the CPU has executed the stop command, the program terminates. Let's summarize. To tell the computer what to do, special commands had to be used. These commands can be understood as words of a language. In order to be able to program the computer, we need to learn a specific artificial language. Such a language is called a programming language. More about this in Module 4. We wrote our program in a hardware-oriented programming language, since memory cells in the main memory and registers within the CPU were addressed. Each command uses certain keywords, such as load and store, which roughly explain the effect the command has on the program. In our example, we have used a fictional assembler language and a fictional set of instructions. In reality, depending on the type of computer, a different command set and therefore a special assembler language must be used for programming. Since an assembler program is not really easily readable and understandable, so-called higher programming languages were developed in the 1960s, which are easier to learn for humans, because the used commands were adapted to the natural language of humans, and one does not have usually to worry about memory addresses and registers. In the next modules, you will learn about some specific higher programming languages.